Hi, and welcome to this presentation about the fascinating world of sensor fusion. My name is Cristina Rico, and I'm the head of sensor fusion at CARIAD. We are the automotive software powerhouse of Volkswagen Group. And if you know a bit about Volkswagen, you will know that it's one of the biggest OEMs in the world. So if you like AI, you will immediately recognize the power behind Volkswagen to acquire data. CARIAD is an internationally positioned technology company. We are already working together with development teams in the US and China, and we are currently establishing our subsidiaries there. Currently, we are around 4,500 employees and growing fast. So, if you're interested in working with us on sensor fusion or with any of my colleagues, let me know. ADAS ID is a key area for CARIAD. And my team and myself, we are working on a project that will be crucial to the introduction of high levels of automation to the road. CARIAD aims to develop level 2, level 3, level 4, and even beyond features for AD. We will all gain back so much quality time in our cars. Can you imagine sitting back and reading a book or enjoying a movie while the car will drive itself on the highway? But we will only reach this level of automation with a significant transition. For example, from classical sensor fusion to more advanced technique like AI-based sensor fusion. Otherwise, we won't be able to achieve high levels of automation. In my presentation, I will show you why. Sensor fusion is a key task in autonomous driving software stack. It brings together the information from different sensors and generates the first step of the so-called environment model. The environment model describes a comprehensive view of the vehicle's surrounding. Sensor fusion algorithms should ensure spatial and temporal consistency. On the one side, we see the input, typically sensor perceptions like camera, LiDAR, radar, or ultrasound. But we can also have others like information from the car-to-car communication system. How the exact interface to the sensor fusion algorithm will look like will depend on the approach used by sensor fusion. During this presentation, we will compare two different approaches. On a side note here, there are many approaches for sensor fusion today, and it is a very exciting discipline that is now rapidly evolving in a quite a radical way. Sensor fusion is not yet at all state-of-the-art. On the output side, you see the resulting product, the environment model, which we can classify in different subproducts. The static environment model describes all static raised objects like walls or parked vehicles. The dynamic environment model describes all potentially moving objects like pedestrians or cars. The drivable area, for example, is free space or the passable area. And last but not least, we have the regulatory environment model that describes all the elements that have illegal relevance, like lane markings or traffic signs. So, if you want to do sensor fusion, there are many ways to solve the task. The following are 5 criteria that you can use when selecting a fusion approach. The sensors you are using and how to fuse them, monomodal or multimodal, the safety concept, which refers to the robustness of the system, the fusion level, high level, middle level, low level, the data availability, and of course, the algorithm technique. Today we will focus on the algorithm technique, and we will compare classical approach versus deep learning. From now on, I will say AI, but I mean deep learning. Now the question is, why do we need AI-based sensor fusion at all? I guess I'm not here in the place where I need to convince the listeners, you, about the benefits of AI. Nevertheless, this question will always arise, as there is always a cost implicit when shifting to a new technology. and the investment has to pay off. There are two main reasons why it is a good idea to use AI in sensor fusion. The first one is that for the same target performance, when using AI technologies, we can scale faster. The reason for it is that especially when high performances are required, the number of exceptional cases or corner cases that have to be taken into account is higher. Having coders that have to think about each one of them and find hand-coded algorithms requires a lot of time and human resources. It's difficult. Sorry, here we humans have some limitations. This is why in the top right of the graphic, you can see how the improvement of the performance is flattening for high levels of automation. The second reason is that in general, we can achieve high levels of automation. You can see it in graphic how once data-driven development starts, the reach automation level is higher because we can achieve a better performance. But of course, not everything is going to be an advantage. Data-driven development needs, surprise, surprise, data, and a lot of data. We save in human costs for hand-coded development. However, we will have more costs for data acquisition and labeling. There is a good thing here, and it's that for other parts of the software stack, like perception, especially for camera and LiDAR perception, the usage of data-driven development is already state-of-the-art. This means that the data acquisition strategy is necessary and not only from sensor fusion anyway. So here you have a point to start with. In CARIAD, we call the system responsible for the data collection the big loop. I recommend you to have a look to the presentation of my colleague, Stefan Sinklinger, who is responsible in CARIAD for this topic. Let's have now a look to AI-based sensor fusion. So in this video, we show an example of AI-based sensor fusion for 3D object detection. On the left side of the video, you can see how the camera image looks like. The camera perception backbones calculate the camera feature maps. Afterwards, they are transformed by an autoencoder into bird's eye view. This is in the bottom left image. In parallel, a LiDAR backbone computes feature maps from point clouds represented in bird's eye view, which are shown on the bottom right. Now, since the feature maps of both modalities are in a common space, they can be fused to provide improved feature maps to the object detection head. In the middle of the video, you can observe the results of the multimodal object detection. Let's have a look now on how our sensor set looks like. Safety is very important for CARIAD. Therefore, we maximize information sources in order to ensure the safety of our customers. We have integrated a whole camera belt around the car, and the data is processed by our own in-house video perception, my colleagues. Not only that, parallel to the camera belt, we have additionally installed a radar belt which samples everything with its non-line of sight sensor principle. A laser system is able to scan the distances with high accuracy and high resolution. Additionally, we have ultrasounds and also other sources of information like car-to-car communication. Now, before going in more detail into the AI fusion architecture, I will show first the classical object-level sensor fusion architecture so that you can compare both of them. In the classical sensor fusion on object level, independent network backbones and heads predict objects for each sensor individually. Afterwards, sensor fusion receives this objects list and fuses the individual objects in order to provide one unified list containing the fused objects of all the sensors. One drawback of this fusion strategy is the late combination of information. If two or more sensors have partial information about an object, it might not be detected for any individual sensor. However, if the partial information is already combined on feature level, and the combined features I provided to an object detection head, the object will likely be detected. This is exactly what AI sensor fusion does. Let's have a look to it. The solution for the previous mentioned drawbacks of object-level fusion is AI fusion on feature level. Instead of fusing objects listed on different sensors, information are combined already on feature level, and predictions are made only once and on all available information and not for each sensor individually. The foundation of AI-based low sensor fusion are feature maps on the individual sensors, which are extracted by independent network backbones. The Spatial fusion transforms these feature maps into a unified space and fuses them together. The result is a unified representation of a vehicle environment containing the information of all the sensors. To incorporate time as an additional source of information, and we don't want to lose any information, a temporal fusion step additionally exploits the output of the spatial fusion from previous time steps in order to further improve the feature quality and compensate missing features. This high-quality feature-based representation on the environment is then provided to the heads, which compute predictions for different tasks and other functions. So now we are going to have a closer look to the spatial sensor fusion, which is responsible for generating multimodal features in a unified space. This is based on the individual sensor feature maps. Since all the sensors feature maps live in their respective sensor space, a transformation step is required to transform them into a unique space. A crucial decision here is the choice of the unified space. On the one hand, it must be possible to transform the feature maps from every sensor in the unified space by a fixed geometric or learned transformation. On the other hand, the feature maps provided to the heads are in that unified space, so it also has to fulfill the needs of all heads and their related tasks. A commonly used space here is the bird's eye view that you have seen in the previous video, combined with a learned transformation based on a transformer network, which learns a data-dependent transformation from sensors to bird's eye view. After the transformation step, the feature maps of the different sensors are fused by a multi-scale sensor fusion network to compute multimodal feature maps, which are then passed to the temporal fusion. So we go now to have a look to the temporal fusion, which follows the spatial fusion. This temporal fusion is very important because time is an additional source of information. To give an example, areas occluded in the current time step might have been perfectly visible in other previous time steps, for example. Following the same argumentation than for sensor fusion, temporal fusion on feature level provides the same advantage over temporal fusion on object level. Therefore, a recurrent fusion architecture fuses current and past information on feature level. The key component is a temporal memory, which aggregates and transports information over and through time. Looking at time t, the temporal memory from the previous time step is temporally aligned by fixed or learned transformation to compensate ego motion and object movement. The aligned temporal memory is then updated with the current feature maps, which are provided by the spatial fusion. Finally, the memory is forwarded to the heads for the multitask prediction and also passed to and reused in the next time step following the recurrent pattern. This recurrent strategy decouples the runtime from the number of exploit pass frames. So now we see the last step on the architecture, the headers, and the results of the presented fusion step before is a high-quality multimodal feature map in a unified 3D space. Since an environment model for autonomous driving must provide a variety of information about its environment, like dynamic objects, drivable space, or traffic signs. Therefore, we need a multi-head architecture and training. Every individual head is trained for one specific task, like 3D bounding boxes, prediction for object detection, classification of traffic sign, or road segmentation for detecting drivable space. While multitask training comes with additional challenges, it also provides valuable benefits. Since all heads operate on the same features, the network cannot focus on one task but has to learn a more generic feature representation, which fits the needs of all the tasks. As a result, many tasks benefit from this improved feature representation and achieve better performance compared to the single task training. One related challenge, however, is that some tasks may have contradictory needs, which make improving both tasks challenging. Once we know the basic architecture, where to start? The first step is to choose a practical project that offers the most benefit, but it is also a low-hanging fruit. In autonomous driving, functions can be clustered in 3 categories: driving, parking, and active safety. We need to analyze each function for AI-relevant assessment criteria. Like with most AI-based projects, training data is a major issue and especially challenging because a huge dataset is required. This dataset contains the data of all sensors and additional labels for every task. An ideal initial function would have a reduced sensor set and only 1 or 2 required tasks, which both reduce the dataset requirements and labeling efforts drastically. Additionally, focus on functions where neural networks shine and classical approaches do not achieve convincing results, because it is important to improve existing systems and not only replace a classical approach with AI, so technology for the sake of technology. Finally, a lower ASIL level also makes the first function easier from a functional safety perspective. Here we can see how we would proceed when comparing 2 generic functions. Function 1 has SOP 2028. Function 2 has SOP 2025. From the benefit perspective, we will see that function 1 would benefit more of using AI-based approach. However, if we analyze the rest of the criteria, we will see that for function 2, we will develop it in a much easier way. Additionally, the ASIL level of function 2 is lower. And that's why we start with this one to learn, and then we can change to the first function and achieve the higher benefits. The training of a complex architecture like this, which consists of a large number of components, is challenging. It gets even more challenging when single sensor heads are required in parallel for redundancy. There exist 3 potential training strategies, all starting with the training of the individual sensor backbones with the single sensor heads. The next steps depend on the chosen strategy. The first one ensures excellent single sensor performance by freezing the backbones during the training of the fusion network and heads. However, the performance on the fusion heads will be inferior in this scenario. The second strategy favors fusion performance over single sensor performance by adapting the backbones during fusion training. Afterwards, the sensor heads are retrained with frozen backbones to adapt to these changes. The last strategy trains fusion and single sensor heads jointly, which makes the training procedure more challenging, but allows for the best combined performance of fusion and sensor heads. That would be kind of start. However, at some point, the challenges between perception networks and fusion networks differ, so we need to handle them separately. So with this, we have now come to the end of the presentation. I hope you have enjoyed it. I hope you learn a little about it, and thank you.